introduction. Good morning and welcome everyone. It is an honor for us to be here today presenting Flink Forward. Especially for me, I gave my first Flink presentation around 8 years ago. Back then, Flink was in its infancy, and it was the age of big data, and mostly Flink was deployed in large Hadoop clusters. 8 years after, and we're here all witnessing a rebirth of interest in Apache Flink. This time, though, the age is of cloud computing and cloud-native application. So when our team had to face the challenge of providing Apache Flink at our organization, we asked the question whether Flink was ready for this age. Specifically, we wanted to know, is Flink ready for the age of cloud-native application where you can apply all the automations and practices and techniques that we use in our standard services? And can we take a bare bones application of Apache Flink from a simple application to get developers started building Apache Flink to production all the way in 5 minutes or less? So in today's presentation, we want to share with you the journey and our team's answer to these questions. We're going to share with you the principles we followed and also the challenges we faced.
All right. Let me set the scene by telling you a little bit about CashApp. What is it that we do, who we are? So this is CashApp on the screen for you. Cash is a part of Block, and we started as a way to send money between two people. So in that regard, we are a peer-to-peer money transfer app. It's grown way beyond just a peer-to-peer system and expanded to add a suite of financial products like physical virtual cards, deposits, Bitcoin buying, selling, investing, taxes, and many more. So we provide economic empowerment for our customers, especially by serving the underbanked. We are live in the US and partially live in the UK. Well, I could go on and on about Cash, but that's for after the keynote coffee conversation. But show of hands, who here uses CashApp? Wow, that's a lot. For the rest of you who are in US, we need to fix that. All right, so Cash has, behind this rich set of features, there's a complex architecture. If I should simplify it, I would say it this way. Cash evolved from a few monoliths to a large services. And all the services are constantly communicating with each other via synchronous calls, yes, but predominantly via the eventing backbone, which is built on top of Kafka. And these services are constantly sending huge amounts of data related to payments or card transactions, identity verification information, or even customer information, and a lot more. And the services who are using this information and the data are using it for the purpose of machine learning, like fraud detection, reconciliation, tracking Cash's money, and data warehousing, like for analytics, and many more. Oh.
So once we started in this journey of migrating from the monolith to event-driven architecture, we noticed that there were lots of solutions out there that to implement the use cases that Rashmi just mentioned, that were an inefficient ad hoc implementations of what a streaming processing framework would provide you. So we had services and data stores and other services that will do some filtering or event enrichment and put that result into our data stores, and then have another service that could be triggered by on schedule or by RPC calls, and then do some SQL aggregation and put that data into another data store or object store. So we quickly realized that of all the services, we could simplify those solutions by using Apache Flink. Also, Flink, as we knew back then, had integration points for most of the services that we were using at the cloud at the time. And we decided to use one of the solutions provided in the cloud platform that we were using. And for the most part, that worked really well. However, very quickly, we ran into issues. We had to assess whether having a cloud provider service was the right solution for us, but we didn't have access to the latest Flink versions. We also couldn't customize our deployment. So we operate in a really constrained environment, highly regulated, with tight security constraints. So we wanted something that, a solution that would give us access to the latest versions, but also that will allow us to customize the deployment of Flink applications. And we also wanted a solution that would allow us to manage those deployments in an easy way. So we analyzed all the options. That was around 2 years ago in the market. We needed to deploy our clusters in our the Flink applications in our Kubernetes clusters. And we had the expertise, we had that expertise in our cloud platform teams. Of all the options available, we decided to use the Ververica Platform. Coming from the creators of Apache Flink and looking at the features it provided, we decided to go with Ververica. It gave us a declarative approach to deploy Flink applications. It also provided API endpoints that we use to hook up with our automation processes. And I think from the perspective of providing Flink, a Flink platform, it was very closely matching the latest Flink versions, which was also something that we wanted to have.
Right, so onboarding a new technology is not an easy feat for any organization. So we were a platform team, and for a platform team, what's important is to empower our engineers by providing a self-serve tool that is secure, stable, and most importantly, provides helping with developer velocity. So we had a set of guidelines, guiding principles in our organization for building regular applications, and we reapplied this for building Flink applications and provided bootstrapping for building Flink applications, making provisioning simpler and operations easier. So what goes into building Flink applications at Cache? So there are 4 components to this. The libraries and the app template focus mainly on the building Flink application part, and the CLI tool and the CI/CD pipeline focus mostly on the deployment and operations. So I'm going to be talking about each one then. So the Cache Flink libraries is a thin layer which provides a collection of Flink libraries which is packaged together. And these libraries are going to help in making the building of the Flink applications easier for our engineers. So via this layer, we provide libraries for like serializing, deserializing events, like Flink testing, metrics reporter for observability, and feature flags for rolling out, and etc. We provide support for multiple Flink versions, which kind of match the Flink version supported to us by Ververica, so that the engineers can pretty much choose the library package version that supports or the important for their the version of Flink app that they're building. The next one is the app template. Like the name suggests, this is an exemplar that provides a scaffolding around Flink application. So the engineers can use a simple one-line command and initialize a brand new Flink app from scratch in less than 5 minutes. That's important bit. Along with getting a simple or a basic Flink application, they get an application which is having a Kafka source and an S3 sync or a print sync. The reason why we choose this as a default is because a lot of use cases in Cache revolve around having Kafka as a source, but this is very easily customizable. We provide guidance and documentation for our engineers to do that. In addition to these advantages, they also get access controls and certificates that are required to run these applications and deploy them later on. And also now the engineers can focus on writing the business logic instead of worrying about writing boilerplate Flink code and all that. The CLI tool is another set of utilities we provide which facilitate working with Flink applications. So for most part, the CLI tool integrates with Ververica, calling Ververica's APIs in order to deploy an application and managing applications lifecycle, doing checkpointing, finding out the status, and also in addition to that, it provides access to observability, like if engineers want to quickly open up their logs for their application. And also we create and manage secrets like application-specific secrets, so they can easily mount it on their, automatically mount it on their Flink pods so that they can natively access that. And final one is the CI/CD pipeline. At Cache, we use BuildKite for CI/CD for regular applications, so we just reuse this for Flink applications as well. A basic pipeline that we get along with any Flink app that is created via the template has build, test, and releasing to S3, releasing the artifact to S3, and deploying to Kubernetes via Ververica. But this is easily customizable as well.
Excellent. So at this point, we were able to bootstrap and get something happening in the pipeline as we used with traditional applications. Let's take a look at how we managed to simplify the deployment for our engineers so that for them it was really easy to get started. As a platform team, we wanted to be fully self-serve and just enable and unlock all our product teams using Apache Flink. So again, we, in this case, leverage a tool that is built in-house. I'll talk a bit more in the following slide. But this tool provides a declarative approach for engineers at our organization to provision any type of infrastructure that we provide. For this particular case, once we decided to roll out the Ververica, and in fact, for the previous Flink offering that we were using, we used the same manifest with minor changes when we migrated over to Ververica. But this is very simple. It uses the HashiCorp configuration language. It could be any configuration language for that matter. But it allows you to define multiple Flink applications. And to get started, you only need to provide the build binary version from your build pipeline, the Flink version that you're going to use, and the desired state of the application. So just with this minimal manifest, our provisioning tool will create a Flink cluster in Kubernetes through Ververica. We also provide, via the manifest, the option to extend the configurations, and that happens pretty soon once you put an application in production, so you can create or extend the Flink configuration according to the use case, as well as the Kubernetes resources for CPU, memory, and storage. At the last stage of the pipeline, our provisioning tool, which it's quite simple. It's a Golang application that is interfaces with Terraform, Kubernetes via Helm, and any software that provides an API. It takes in the manifest and creates the required resources in AWS and Kubernetes so that at the end you have a functioning and running Flink application. But for our product engineers that are creating right now Flink applications, they pretty much don't care whether the Flink job is running in AWS or Kubernetes. For the most part, they have access to previously the Flink UI only and some of the dashboards. Now we have the Ververica UI that gives a good set of information around the state of the Flink application, and it does cover some of the configuration for Kubernetes as well, and from there you can access the Flink UI. The last part that we provide, and intentionally we do so from the application template, the exemplar application template that we provide to our engineers, it already contains configuration to hook into our observability dashboards. In our case, we use Datadog. It could be any platform, but we make sure that at least the engineers get the most relevant metrics for them to debug and troubleshoot Flink applications, which is something that happens pretty quickly once you go into production. Flink requires expertise. So that completes our rollout, and it has been working for us really well. We have lots of teams that sometimes I go to the Ververica dashboard and realize, oh, some people are creating Flink applications, and I can see now that happening. And we, as a platform team, we are not the bottleneck. We are not in the middle of that process. So that's really encouraging. However, we did run into some challenges doing this, as Rashmi mentioned, as probably you know, rolling out a distributed systems platform in any organization, regardless whether you put it on the cloud or you use another cloud service, it requires lots of work. in our particular case, in Cache, we deploy our services using a service mesh deployment architecture. People familiar here with the concept of service mesh? All right, I'll quickly explain. So we deploy in Kubernetes as well. I imagine people are familiar with Kubernetes as well. So the way we deploy our Flink jobs in Kubernetes, we use a service mesh. It is a deployment architecture in which the main processes communicate with each other and the external world via a proxy process. At Cache, we're using Istio, which is one of the many solutions for service meshes out there. So in this case, the pod manager, so the pods, which contain the task manager and the job manager, they use Istio to communicate with each other and also with the external services. Back then, we were wondering whether this was a good idea. The reason why we wanted to do this, and it's something that we couldn't do with a previous cloud service provider, as I mentioned, we operate in a highly regulated environment. We have tight security rules. We wanted to leverage the existing traffic policies that we use with Istio for our services in Flink applications. So we use the customization in our deployment that is allowed with Ververica Platform, and we injected an Istio proxy. This allows us now to implement event enrichment use cases by calling out from a Flink job to other Cache services, and also specify the dependencies so you cannot call out to any services. You have to have the permissions in the traffic rules. And we also control the traffic outside of the Flink cluster to any external services. So it's not easy for someone to decide in your Flink job to store data or the results in, I don't know, GCP, it could be S3. All that has to be properly configured in our traffic policy. So doing this with Istio has worked with us really well. However, we did run into some issues. If you are trying, I don't know how many people are trying to deploy Flink as a service mesh, but in Kubernetes, unfortunately, there was no support at the time to control the life cycle of these sidecar proxies. That's how they're called, sidecar containers. These are containers alongside the main processes. And when we're doing job upgrades or application updates of Flink, deploying new versions, it would take a long time because Ververica will shut down the Flink job, the job manager and task manager will terminate, but the Istio proxy will hang around, increasing our deployment times. And initially, we couldn't understand why, but then we realized that there's not enough support in Kubernetes to manage properly the life cycle of sidecars. But thankfully, the latest versions of Kubernetes, I think 1.28, now they have native support, so probably we can solve this issue. We had to provide our own solution in the meantime, but this is something that is solved now. The other issue we found with Kubernetes, and we didn't think about it properly at the time. As you know, Kubernetes is a scheduler of containers, so it schedules the pods for your Flink application across multiple nodes in the Kubernetes cluster. But then our core infra compute team will come and do Kubernetes upgrades or restarts that we do periodically for compliance reasons, and it will impact our Flink applications. And I think it's because of the nature of Apache Flink architecture and the way it's been designed. Whenever you lose a task manager, your Flink job will restart. So if you have 100 pods or a large number of pods across multiple nodes, when the cluster is restarting, the Kubernetes cluster is restarting, or the node is restarting, it impacts your job. And we've seen this in some of our larger Flink jobs for data warehouse ingestion, where you see a huge impact of the job restarting, and then you get paged. So we're thinking now of using something that is called in Kubernetes pod affinity, and applying affinity rules so that we can compact and deploy as much as it is possible using the least amount of nodes, the pods for a particular Flink job in the Kubernetes node. So hopefully that will reduce the impact that we're seeing when we are doing Kubernetes node upgrades and restarts.
Okay, so while we are in the theme of challenges, I have one or two more. So the use cases that we have in Cache, it's hard to predict the traffic. So consider customer signups or even on-peak, off-peak data. So it's always varying. So how do we think about scaling our systems in this case? If we over-provisioned our systems, then we are wasting our resources. It's doing more harm than good, yeah. If we under-provision them, then we are running into the risk of having slowed consumption and worst case, maybe lose data. So with obviously no-brainer, the auto-scaling would be the right solution, scaling the system up and down based on the traffic pattern. I'll talk you through one of the incidents that we had recently with Flink. For one of our use cases, one of our syncs, which was writing to an S3 somewhere, was throttling totally, and then that was causing a back pressure on our upstream operators, and then that would slow down our consumption or like the source which was consuming from Kafka, and then we built a lot of lag. So at this point, our engineers, we had to jump in and then pull some levers and update some parallelism of the operators and tune it in different ways, and then finally get the system back up running. This would be an ideal scenario for auto-scaling to kicking and to help us. Unfortunately, we do not have that working right now. We're still working on it. We're right now experimenting with the autopilot from Ververica, and we are trialing out the recommendations of the scaling patterns that we're getting from that. The other challenge that we have is related to deployments and upgrades. So what happens is, as we all know, Flink requires a restart when there is any change in the job. And that kind of doesn't sit well when we have use cases with higher availability. And also, what if the deployment has a problem and then the deployment downtime is going to increase even more? Well, we tried and we solved one of the problems, which is gaining a little more confidence into our deployment by implementing a variation for a blue-green deployment. The reason I say it's a variation for blue-green is because it mimics the traditional blue-green, but with a twist, and this is how it works. Like Karel was explaining, we have a deployment manifest, and in this case, we'll define a blue and a green application like Flink app in the same manifest. And when we do a deployment, first the deployment goes on the blue, and then the green is still running on an older deployment, and then blue does a checkpoint. At this point, we verify checkpoint is successful, and all is well, and then we finally deploy the same application on green, same deployment on green, and blue is suspended. We do not want to keep it running anymore. And then finally, green does a checkpoint, and then all is well. So yes, this doesn't solve us the problem of having downtime. We still have a downtime. But what this helps us solve is gaining that extra confidence in our production deployment. But at this time, we know that there is no issue with the production deployment. This is not the recommended pattern that we provide, but it's a tool of convenience. The teams in our organization have used this in some creative ways, like some teams for some use cases have used the blue environment as a no-op sync, so they're not writing duplicate data to the same sync. And in some other cases, like the green application is writing to the actual Kafka topic, while the blue application is writing to a test topic. So it's kind of used it in different creative ways. And we've heard feedback that kind of we've caught production issues, like before, pre-production issues, by testing still on production because of some poison events or if the deployment was really bad. Well, as we get to the close of our talk, I would like to touch on a few things that we have said so far. Flink is the most powerful open source stream processing engine, yes, and by far the most widely used, but it requires expertise. And the way we have tackled it in our organization is providing the bootstrapping mechanism so that the deployment and adding all the guidance and the documentation, doing kind of tutorials for our engineers so that it helps with the development process. We've embraced the declarative approach for provisioning our Flink apps, implemented infrastructure as code, and even had the strategy to get confidence in our production deployments as well, the blue-green variation thingy. But zero downtime deployment is definitely an opportunity for future improvements. And finally, there's substantial progress with scaling Flink applications. Auto-scaling has come a long way. AWS KDA had auto-scaling from Flink 1.13, and with the reactive scaling, from Flink 1.15 and Flink Kubernetes operator. There's a lot of progress there. And we are keeping an eye out on what is in the roadmap. We feel there's definitely more things, exciting things that are coming, that especially the Flink in-place scaling, that's going to be a huge game changer, I believe. And that's it from us. Thank you for listening to us today.